Welcome to Phoenix Analysis and Design Technologies, where we make innovation work through simulation, product development, and rapid prototyping. As an ANSYS channel partner, we sell and support the full suite of ANSYS tools in the Four Corners states and Nevada. Our headquarters is in Tempe, Arizona, while we have offices in Littleton, Colorado, Albuquerque, New Mexico, and near Salt Lake City, Utah. In addition, we provide training, mentoring, and simulation consulting with these ANSYS tools worldwide. Hey everyone, this is Manoj with PADT. In today's focus video blog, I'm going to show you a new trace import extension in ANSYS Mechanical that will allow you to analyze the effects of the copper fraction variance in a PCB without having to resolve the fine features such as the traces, pads, etc. So here we are in ANSYS Workbench, where we can see that I've brought in a steady-state thermal and static structural analyses tied together. Let's take a look at how it looks in ANSYS Mechanical. Here we can see that I have a model of what looks like a PCB, a very simple one. And when we zoom in on the model, we can see that it's actually made up of 11 different bodies, which can represent the different layers of this particular PCB. On top of the PCB, we have a very simple package. Now in ANSYS Mechanical, we have to define a material for the entire body, which means that we can account for the variances in copper fraction distribution throughout a particular layer. Nevertheless, let's take a look. In the thermal analysis, I have a 1 watt heat flow to the top of the package, as well as a temperature boundary condition at the bottom to act as a heat sink. For the structural analysis, I have my 4 corners of the PCB fixed. I've already solved this analysis, so let's take a look at the results. First, the temperature. And as expected, we can see that it's a very simple and uniform temperature distribution with a very small temperature gradient. I changed the scale so we can see how it looks on the PCB itself, and it's sort of expected. When we look at the total deformation plot, again, it's the same thing. It's a very uniform total deformation distribution throughout the PCB. And this is due to the fact that the bodies of the PCB layers are all the same material. Now we know that this is made up of different layers of dielectrics and metals. The dielectric will act as a thermal resistance, while the traces, the pads, etc. act like thermal paths. That can have a significant impact on the thermal distribution and the structural deformation of this particular object. But how can we analyze that without needing to mesh the fine details? Well, we have this trace import extension, which we click, it'll insert in a map trace data into the tree, and the first thing we want to do is scope it to the 11 bodies of the PCB. Click apply. The next thing we need is a trace format. Now that can come from Cadence, ODE++, or in this case I'm going to go ahead and go from IcePack. I'm going to go ahead and browse to the file. Click open. And the next thing I need to do is define the metal and dielectric material. So I'm going to go ahead and choose copper alloy and FR4 epoxy. I'll talk more about the discretization here in a second. I'm going to right click on the object and hit generate. And what it's doing is it's mapping the ECAD trace information from the file that we gave to this 200 by 200 discretized grid, which the 200 by 200 is more than sufficient for most applications. To look at the imported data, we'll go ahead and click on this button. We'll look at the top layer just for this purpose. There's a lot of things we can look at, but the first thing we're going to look at is the average copper fractions. We'll go ahead and say show imported data. And we can see that this extension has essentially mapped the ECAD trace data into a format that can be seen by ANSYS Mechanical. This is a particularly interesting point to note, where half of the package sits on a much higher copper fraction than the other. The next thing we can do is map the data from the ECAD discretized format into the mechanical mesh. And here we can see that. Now remember, this is a smeared property, and so we don't have to resolve the traces, we don't have to map the pads, etc. All we're doing is mapping the copper fractions from the ECAD trace data into the mechanical mesh. I'm going to go ahead and clear the graphics, and we're going to go ahead and hit solve. As you can see, the ability to show the copper fractions and how that impacts the structural and thermal analyses is pretty important. So we'll go ahead and let the thermal analysis solve. Then we can look at the temperature distribution here, and clearly already we can see that it's non-uniform, and it has a much higher temperature gradient. I'm going to change the scale here just for demonstration purposes. And when we zoom in on the package particularly, we can see that half of the PCB that the package sits on is much hotter than the other, due to that variance in the copper fractions. Now let's take a look at how that might have impacted the structural analysis. So I'm going to go ahead and solve the structural analysis as well. This is where it's really important, is due to the variance in the copper fractions, the structural integrity at certain parts of the PCB differs from other parts. And there's no way to model that without actually having to resolve the traces, except through this. So once it's solved, let's take a look at the total deformation plot. And we can see that it's non-uniform, and we can see the variances due to the copper fraction differences in different parts of the PCB and the layers. Same thing for equivalent stress. I'm going to go ahead and change the scale just a little bit so we can get a better picture of how it looks. And there we go. We can clearly see the impact of the copper fraction variance throughout the layers clearly in the equivalent stress plot. This is very significant and provide a huge value to engineers who need to analyze a PCB from a thermal or structural standpoint of view without sacrificing accuracy. Thank you for watching this video. Please subscribe as we'll be doing more videos on tips and examples in ANSYS. Feel free to jump on our website at PADTinc.com or give us a call at 1-800-293-PADT or email us at tech@PDTinc.com.